In this lesson, we're going to talk about helping kids with two-digit multiplication and using base 10 blocks to do that. Traditionally, when we teach kids to multiply, we teach them the algorithm. And so we say 4 times 2 is 8, 4 times 1 is 4, 1 times 2, that's 2. No, wait a minute. My teacher said put a 0 and move the 2 over. 1 times 1, that's 1. And I know that my product is 168. That's the right answer, but if I can't keep these parts in line, if I get confused about what step I'm on, I'm stuck as a student. What I want to show you is a different model. Here I have the same problem set up. Here's 12 on my vertical axis, 14 on my horizontal. We've spread them out a little bit to make it easier for you to see. And I know that the product is the area of this rectangle inside. So I'm going to use my base 10 blocks. 10 times 10, I do have a pointer. 10 times 10, that's 100. 10 times 2, that's 20. 10 times 4, that's 40. 2 times 4, that's 8. So I have my same 168, 100, 10, 20, 30, 40, 50, 60, and 8. This time, if I were to pack all this in tight, it's a rectangle, and it represents the area of the rectangle. Now, we don't want children to always have to go around and use base 10 blocks to multiply. We need to move them from a model like this to a more abstract and a more efficient notation. One of the ways I can do that is by teaching kids to draw. So I'm going to use a red pen to represent my factors. And you can see I'm just using line segments and dots to represent 12 times 14. And now I'll switch to blue for my product. 10 times 10, that's 100. Line segments again, 40, 50, 60, 8 dots. This is something, if I grab just my drawing, whoops, I grab just my drawing and slide it down. This is one of the things I love about the interactive whiteboard. There's what that sketch looks like. I can see what I built, and kids would be building at their desk. I can draw my picture. This I could do on a piece of scratch paper while I'm taking a test. I'd still like kids to get a little more abstract, because this is a strategy that works for two-digit numbers, but not for 3. So I want to move kids to a more abstract way of looking at things. And so if I turn the page, I see different representations of the same problem. Here I have the same 10 plus 4, 10 plus 2 rectangle that I built with my base 10 blocks, but this time I just used expanded notation. So again, I grab my pen. 10 times 10, that's 100. 10 times 4 is 40. I'm simply filling in each block. 2 times 10 is 20, and 2 times 4 is 8. And if I sum those, I get my same 168. I could even go a step further and represent this multiplication problem this way as an example of the distributive property. And we'll come back to that in just a minute. From here, I need to come to here, because I still don't want to see that when my students are doing multiplication. I'm going to repeat this general algorithm now, but I'm not going to lie this time, because I told some lies. I didn't name some numbers properly before. 4 times 2, that really is 8. But that wasn't 4 times 1, it's 4 times 10, and that's 40. 10 times 2 is 20. 10 times 10, that's 100. 168. I can see all of these numbers over here. This becomes a shorthand way of doing this. And even if these were 3-digit numbers, my rectangle would simply be larger. My list of products would be longer. Let's come back to this representation and think about algebra class for a minute. What I did in filling in each block was FOIL, that we remember from Algebra 1, where I take the first term times the first term, the outside terms, the inside terms, and the last term. The only difference is that in algebra class, instead of these 10s, these will be x's. So I have x plus 2 times x plus 4. Or, if I want to represent it up here, x times x is x squared, 4 times x is 4x, 2 times x is 2x, 2 times 4 is 8, and I could sum those to get x squared plus 6x plus 8. I'm not going to teach kids the algebra part when I am first teaching them to multiply, but it's powerful that I'm teaching them a model that will carry them all the way through to an algebra class.